Okay. Well, why don't we get started today? I'm going to start things off today, but I'm going to leave Damick to finish us off for today because, the daycare interferes with my seminar. So we're very delighted to have Dan Bienstock from Columbia, who was the Liu Family Professor of Operations Research. And I recently stumbled upon one of his books on sort of the electrical transmission system, and it's actually a very, very good read. So people should pick that up. And one of his students is actually here, who has joined us, Akte, who joined us a year ago, which Dan says is his favorite student by far. So without further ado, we'll hear from Dan on his work, Complexity and Exactness in Polynomial Optimization.
Well, thank you very much for the invitation. It's very nice to visit Cornell, even if vicariously. As I explained when I received the invitation, this is work that is very much in progress. I would like to fill the entire 45 minutes or hour with new theorems, but I can't. I'll give you some theorems without proofs and instead explain the background. I will be very bipolar or multipolar in this talk. You'll see that I switch perspectives multiple times. And I will attempt to make this into a multimedia talk. Let's see how that works. And this is the new work is joined with these two very bright younger colleagues. Okay, see, I'm really screwing up. Come on, there we go. All right. So the theoretical context is what many people are today calling polynomial optimization, which means optimization of algebraic expressions subject to algebraic inequalities. Actually, Jim might know, I mean, sometime in the past, it used to be called algebraic everything, and at some point it became polynomial optimization. In the world of mathematics, they would use the word algebraic. This type of problem has been around for a long time, but recently, in the last decade or less, it has acquired a lot of impetus. There are big communities doing this in a serious way, both not just theoretical, but also from a computational standpoint. There are computational packages that are growing in sophistication, and we maybe will see one or two running. And there are applications in science and engineering that are driving this. And we'll see one of them. And the problem instances that people want to address are large, millions of variables potentially, and very complex. And maybe I can make that more precise. And because we are dealing with nonlinear and non-convex expressions, there's the issue of inaccuracies that in solutions and not well understood. And so, as I said, this is ongoing work and background. So now let's spend a few minutes with the nerdy part of the talk, which is the math. Okay. I'll have 3 slides with unexplained math. And then the rest of the talk, I will try to explain why we are doing this and what the results mean. So let's say we have a feasible system consisting of linear inequalities that give you a polytope and a single polynomial of degree 3. And all the data is integral. Okay. So what is the theorem? Again, totally, the context is unexplained. So we can show that it's strongly NP hard to test if this system has a rational feasible solution. And by feasible, we actually mean feasible, not approximately feasible or sometimes feasible or mostly feasible, but actually feasible. All right. Now, when f is linear, well, the classical theory of polyhedra shows that because the system is feasible, Well, you can find a feasible basic solution. And then it's simply a straightforward result to show that the Gaussian elimination will give you a vector that is not only rational, but in fact rational with a polynomial number of bits in the solution. Okay. What if it is quadratic? So this was actually proved by handled by Stephen Battis around 1990. That showed, well, what he showed is that the feasibility of this problem is an NP. In fact, he showed the same thing, that there's a rational, feasible solution of polynomial size. Since this is a very mathematical audience, let's try to do a quick proof. So f of x is quadratic. So we can say f of x is x transpose, I don't know, let's call it h. Battis would have called it h plus c transpose x. And so, and we assume that this system is feasible and it's a polytope. Actually, the proof will work with a polyhedron, so unbounded, but it's a polytope. So as an NP certificate, we would say in which phase the minimum of f is attained. And in fact, which is the phase of minimum dimension in whose strict interior the minimum is found. And if the minimum is found at a vertex of the polyhedron, then of course it is rational of the appropriate size. So let's assume that it is not a vertex, and therefore it is found in the interior of the face. And because let's say the point is x hat, okay. Because this point is the minimum of f, and it is in the strict interior, then the gradient of the function using reduced coordinates will be zero, okay? And slightly abusing notation in a certain sense. So we will have an equation like this, equal to zero. There we go. But it's really in the reduced coordinates in the face that is equal to zero. Okay, now, if in the reduced coordinates, this the matrix H, it's not really H, but let's say let's call it H. If it were invertible, then we are back in the same game that the point x hat is uniquely determined and it's rational and with a polynomial number of bits. And so let's assume that the matrix H in the reduced coordinates has a non-trivial null space. And so you have something like this: H times V is equal to 0 for V in that space, in the affine hole of the face. All right. Now, if V has a non-zero inner product with C, then this will contradict the assumption that x hat was the minimum, because you can move a little one way or the other. The quadratic part of this function will not change, but the inner product with the C part will give you, if you move in the right direction, a negative number, and so you decrease the value. And so you must also have that V transpose C is equal to 0. And then a simple calculation says that the entire lineal space of V is one where the quadratic has a constant value. Okay, no matter how much you move along this vector V from x hat, the quadratic will not change value. And now, because you're in a polytope, this will take you to a lower dimensional face, and therefore you're contradicting the choice of the face where we were. I'm not sure that Battis's proof was this, but it would amount to something like this. What if you had two quadratics in this system? Well, we'll go to that later. But as kind of coming attractions, going from one quadratic to two is a big change, and going from two to more than two is an even bigger change. All right. Here's another theorem. Basically, it's the same proof. Now we have a feasible system where you have a number of quadratics, but just quadratics plus a polytope. But you know that this is feasible. Then it is strongly NP hard to test if there's a rational feasible solution. Okay, so the system is known to be feasible, but it's strongly NP hard to test if there's a rational feasible solution. The number of quadratics is not big. I didn't try to optimize this. It has to be more than one, because with one we have Battis's result that is positive always. There is always a rational feasible solution of polynomial size. I don't know how big M has to be, not more than 7. All right. So that's what I wanted to say there. And yet one more theoretical statement. Now we have a system like before of quadratics plus a polytope. And I'm stressing the tope part that's bounded. And you know that the system has rational feasible solutions. This is unlike what we had in the previous page, where you knew that it was feasible, and we proved that it's hard to know if there are rational feasible solutions. Now, you know that there are rational feasible solutions, but what is strongly and be hard to test is if there's a rational feasible solution of polynomial size with a polynomial number of bits. And now the number m, the number of quadratics is I cannot make it small. Okay. All right. So this is now that we have dispensed with the mathematics, let's move to the fun part of the talk. And why are we doing this? So now here we have a what people in the polynomial optimization community and maybe others would call a QCQP. It's a quadratically constrained, well, in this case, linear objective problem. And this is in the LP format. It's self-explanatory. The square brackets, this is something that the optimization systems, the packages that solve these problems require you to do. I don't know why they require you to do it, but they require you to do it. It would not be a heroic act to write software that can read the correct expression without the brackets. But this is all that it is, that the free variables, these two, that refers that they are free to be negative, and the others are all by assumption required to be non-negative. So it's a very small problem. It's low dimensional. It has 7 variables altogether. Very small. I don't see any numbers there that scare me. All the numbers are nice, simple, small. So why is this of interest? Well, if you give this problem to various packages, in fact, if you give it to any package that claims to solve these problems, like Gurobi now has a solver. Gurobi can read exactly this. I like Gurobi very much. I use it all the time. Same with Skip. Skip is a different package. I also use it all the time. Excellent. Okay. They will tell you that the value is about that. In fact, they want to say that the value is minus square root of 2. The problem was deliberately concocted to con the codes to convert to what should be an irrational number, thereby getting into trouble. Okay. But they will claim that this is the value. This is a minimization problem. They claim that this is the value. However, upon closer examination, you see, no. The true value is minus 1.22. And at risk of sounding trivial and repetitive, what's happening here is that these packages are giving you a super optimal solution, not suboptimal. It's not that they failed to give you the best solution. They're being a little bit over-eager. They're getting carried away. They're giving you a solution that is slightly infeasible and very super optimal. And this is something that various communities, even communities in engineering domains, have known for some time, that in a nonlinear, non-convex problem, getting a little bit of infeasibility will buy you a lot of super optimality. And one should deal with us. Let's see if we can run this. Now this, I said this is, by the way, this is unbeknownst to us, this is a computational talk. Let's see if we can run this. Where is this? Here we go. Where is this? Okay, here we go. Can anybody see this, or is the font too small? Is that okay? If not, I can do it here, slightly bigger font, but I assume you can see. Here it is.
I think we can see it then.
You can see it?
I can't see it.
Yes or no?
Yes.
No.
Oh, okay.
Mike Todd says no.
Oh, okay. No. All right. So let me do it here. Now this one should be a little bit better. This is it. Okay, there we go. So let's run it with Gurobi, and let's see what it says. Is this the one that well, whatever. Yeah, let's do this one. So it's going to read this. Oh, no, not up. See, this is me. Hold on. There we go. All right. So it ran. This is Gurobi running. Okay. And here you see this is the value. It did some kind of branching. This is the methodology that Gurobi has. Very quick. It found the true solution first, but it discarded it in favor of this better solution. This is the solution that we see over here, all the variables that are not zero. Okay, what else? At the top of the page, you can see this is Gurobi 9.1. This is the beta. This is the latest version, which is much better than the version before. Here are some statistics about the tolerances and the violations that it perceives. One constraint is violated in the 8th digit somewhere. Let's run skip. I can just run it this way. This is a Python script that runs script. Okay. It produces a lot of output, same outcome. Okay. This one, if you look in, carefully at the variables, at the other variables, at these auxiliary variables, this sneaky was not there in Gurobi, but it's here in skip. So we saw that happened. Let's go back to this guy. Here we are again. Okay. Oh, this is a little too big now. Let me go back to this and view it properly. It is on full screen. Whatever. Zoom in. All right. Hold on. All right. So this is a projection of the feasible region to x1, x2 space. Let me go back to, come on, here we go. x1 and x2 are in this part. The second part of the formulation is what's making something happen. There we go. This is a projection of the feasible region. The optimum is right here, and it's unique. Moreover, if you were to make small changes in coefficients, the picture would not change very much, and the optimum would move smoothly. And some people would say that this makes the problem well posed, although I have to say that I haven't seen a rigorous or consistent definition of what well posed means for a non-convex problem. All right, now, this is where the codes are converging to. It's literally off the chart. And you can see that it's nowhere near the feasible region. What's going on? How can such a small problem with well-behaved coefficients cause extremely sophisticated packages to go wrong? And they really are very sophisticated. Both Skip and Gurobi, in terms of their numerical linear algebra, they are not clumsy by any stretch of the imagination. Okay. Now, this is what's happening. This is the problem. Something is happening with my stupid Mac setup. Okay. This is the problem that the solvers think that they see. They think that they see a problem where the feasible region has the two ears that we saw today, plus these two isolated irrational points. And this is where they are converging to. This is where they are converging to, which is both superoptimal and far away from the feasible region. So this is the problem that they think that they see. Come on. But this is the problem. Oh, gosh. I actually don't like Macs very much, I have to say.
You might want to zoom out. I think you zoomed in, and that's what's causing the issue. So just view and then zoom out.
That?
Yeah.
All right. Okay. This is the problem that they have to handle. There was this extra variable sneaky. So the problem that they thought they had to handle was this, no sneaky, but now there is a sneaky. And the second system implies that sneaky must be positive. And it's hard to see that sneaky in any feasible solution must be possible. okay? And even a tiny, tiny positive or non-zero value for sneaky cuts off the point where the solvers wanted to converge to, which is right there, okay? Here the ball has grown a little bit, and that's enough, okay? But I want to stress that the problem that was asked, and here's the true optimum, the problem that was posed is well behaved. The feasible region looks like that, okay? It's not that the problem that was posed is deliberately tricky. No, the feasible region is well behaved as far as one can tell. It's just that with the formulation as given, there is this point which is nearly feasible, but very super optimal. And the solvers are unable to detect this, okay? There are a number of philosophical points that hopefully we can bring up about such problems. But again, I want to stress that this is very low dimensional, with well-behaved coefficients. It's what's really happening is that quadratics already are extremely expressive, are very, very expressive. You can make a system of quadratics say a lot of nasty things, and you wouldn't know it. Okay, now two things.
Yeah.
Yep.
So one thing that I saw in your solver was that the constraint violation was 10 to the minus 8. Is that true?
That's a very good question. Okay. I would have to trust Gurobi that it really is that. Okay. And I suppose in this case, I could plug in the numbers. And verify it. But I threatened before that there are philosophical issues, and I would like to punt on your question. There's a hidden question to Damek's question. And I would postpone that and bring it up in a couple of minutes. And possibly I will not have time. Oh, I hope I'll have time. Well, we'll run the lecture late. So, okay, this will never happen in practice. Okay, these are, mathematicians less talented than Cornell crew saying things like this. Round of error, oh, this is feasible within machine tolerance, whatever that means. Okay, which machine? An abacus? Anyway, now here is, now we are jumping disciplines. Here's a paper that came out a long time ago in the power engineering literature. The power engineering literature being one that has created one of the most compelling applications of these problems, the so-called AC-OPF problem. Algebraic optimization, big, bad numbers, not nice numbers, bad numbers, real life, and so on and so forth. Ian Hiskins, who I know is a very, not just a very talented engineer, he's a very good mathematician himself. He's well-trained in mathematics. I don't know Davey, but him I know, very good. So they wrote a paper where they looked at this network. This is a network, even though it doesn't look like it, has 3 nodes. It's a triangle. And they worked very hard to come up with numerical values, numerical parameters that make sense in the practice. Okay, J is the square root of -1 for engineers. Now, this AC-OPF problem, which I'm not talking about today, in principle, you can formulate it in a network with 3 nodes. It'll have 6 independent variables, but usually people formulate it with dependent variables, so it could be as many as 30. Okay, as many as 30. And what they provided in the paper is a projection of the feasible region to the space of 3 of those variables. And this is what it looks like, okay? There's this part that looks like a tablecloth that somebody is shaking. This is some kind of a donut that's hollow, and I don't know what this is. It's like a Klein bottle, I don't know. I forget whether, so I actually reproduced their results. I forget whether these 3 guys are actually disjoint or not. I think in one of the cases they were kissing each other at an irrational point. The whole purpose of this paper is to argue to their fellow engineers that this real problem that they have to deal with is bad. It's extremely non-convex. It's problematic. And so the notion that these kind of geometric slash, I hate to call them numerical difficulties, arise only in very artificial problems, that they will never arise in a real problem, is bunk. Okay. All right. Now, let's see what else. Here's another perspective also from this power engineering world. So these ACOPF problem, can be formulated like this. Well, anything can be formulated like this. The normal way in which it is formulated is one where these expressions are trilinear expressions involving trigonometric quantities as well as just variables. So you might have something like x1 times x2 times the cosine of x3. And you'll have a sum of terms like that multiplied with very entertaining coefficients of different signs. And you'll have a constraint that say an elegant sum like that is equal to 0. And this is the physics. Okay, this is not some modeler or a businessman. This is physics. This is AC power flow physics. There's another way to formulate the problem where you change variables and now you have quadratics. Okay, the formulation with the quadratics is considered inferior, and it is. But it's an algebraic problem from that perspective. All right. So now there's a competition going on. This, I have a grant. They are in the second round. This RKHS Go competition. The way that they set up this problem mirrors the practice, which is that they don't take this formulation. They add slacks to allow you to violate constraints, but then they penalize the slacks in a very rude way. These are very rapidly growing convex functions. Okay. This shows that they are aware of these issues, that somebody might, a solver might try to cheat by violating constraints a little bit. And they say, well, if you violate my constraints a little bit, I'm going to hit you a lot. Okay. Now, we are still, so I think this makes a lot of sense. This philosophy here provides a one way out of this conundrum that Damek kind of indirectly brought up. We are not out of the woods for the Go competition to address these problems. I shouldn't say solve. We used Nitro. Nitro is a log barrier solver. Log barrier solvers were designed originally for convex optimization. And here they are getting deployed for non-convex problems. There are various addenda, filter algorithms, and so on to try to kick the solver out from local optima. Extremely sophisticated, extremely effective. I was hoping that I would be able to run Nitro or IPOpt on a very big power flow problem today, but the only way I can do it today is through MATLAB. I apologize. And my MATLAB license has expired. And at Columbia, it takes a while to get a new valid MATLAB license. They get, as far as I know, Nitro and the similar package, IPOpt, frequently get a solution that if it's not optimal, it's very near optimal. But of course, with slight infeasibilities. Now, this approach, from the perspective of a solver like Nitro or IPOpt, well, you're not out of the woods, because we give this presentation to Nitro, and Nitro will, it will use the slacks. It'll realize, okay, I can use this. Yes, I see that big steep penalty, but I'll try to use it a little bit. And indeed, this is what it does. However, this entire constraint itself is non-convex because the G is not convex. And so Nitro itself will cheat and will violate this constraint a little bit. And then when you give your solution, the X's, to the engineer will go and compute what he sees to be the true slacks, which will be just a hair bigger than yours. But because the penalty functions are extremely quickly increasing, the penalty that you end up paying could be substantially worse than what you thought that you would pay. Okay, but still, I think that this is a very good idea. All right, now let's see where we are for the next slide. Okay, all right. Before we go to this one, let me make this a little bit smaller again. Come on. Let me show you, oh gosh. Let me show you another problem. Just to show you what else can go wrong. So this is just like what we had before. So I direct your attention to the bottom part. So this is again that thing with distraction and sneaky. The solver wants to set sneaky to 0 in order to cheat. Okay. Now, if we go up here, there are two things that are happening. So this is just like we had before, except that before we just had a single quantity here that was squared. Well, we know this is a sum of squares, therefore it is going to be a square, but the solvers don't reason out this way. And we see the same quantity in the three constraints. So the solver effectively will want to set this sum to be equal to 2. It wanted to set it to be square root of 2 without the square, or minus square root of 2. It'll try to set it to 2, whereas it really should be something like 1.22 squared, which is a lot less than 2. All right, now if we go up here, we see that sum again over here. No, this minus minus. We see the sum over here. So the solver wants to cheat and set this quantity to 2. It really should be a lot less than 2, significantly less than 2. Okay, like 1.44, whatever, 1.22 squared. And now we can see the impact of that. With this quantity here set at a constant, this constraint here is convex, it's less than or equal to. But by cheating, the solver is allowing a much bigger feasible region, less than or equal to 1.44 versus less than or equal to 2. So the solver is actually now changing the geometry of the set of feasible solutions in a very substantial way. And then, with a 2 over here, if this thing here could be fixed to 2, well, this sum and the objective will be equal to 2 divided by 2, so equal to 1. And this is exactly what the solver will do. However, it should be a lot less than 2. Okay, and we can run the solver on this one. And now this is sort of rubbing salt into the wound, because we are taking the original problem and now sneaking it into a higher dimensional space. And it's going to get progressively more difficult for the solver to be able to see these things. So my gurobi.py minbat2 mixed minbat2, what is it? Lifted mixed. There we go. Okay, and it ran, okay, and it says, of course, it's -1 and it's wrong. And notice that sneaky, okay, this is hitting a damic a little. This sneaky, which the solver is treating as if it were a 0, it's not. I mean, this is 5 times 10 to the -4. Please. Okay. And the solver is further annoying you by telling you that it solved the problem to tolerance 10 to the -4. Okay. So with tolerance 10 to the -4, 5.6 times 10 to the -4 is 0. What's going on? All right. Let me run a different one. Hold on. This is another way of using Gurobi. I think it is not. Okay. And what else? We get a little bit more information. Now, this is the same code. Okay, now it says tolerance 10 to the -6. It produced the same wrong value, but somehow it got a little bit more accurate, but not accurate enough. But still, tolerance, there are 2 different tolerances that are being stated. This one here, and somewhere, constraint, this one, 10 to the -10. And yet this is bigger than 10 to the -10. Well, for those of you who have written solvers, and I know that some of you have, anytime that you write a really complicated solver like this one, at the innermost part of the solver, you have some numerical linear algebra routines. And then around that, you build a continuous solver. And now, in this case, Gurobi, around that has some kind of a branch and bound code with cutting planes. When you do that, you have to have a hierarchy of tolerances. And the output tolerance that you would like to achieve has to be coarser than the innermost tolerance that you employ in your linear algebra routines. And in bad cases like this one, the hierarchy is not going to help you because that innermost tolerance cannot be absurdly small. You're doing floating point computation and you're limited there. Okay, all right, so back to the talk. Let's see if this guy will work. All right, so probably not round-off error. This okay, there's some round-off error, but this is getting combined with the non-convexities and non-linearities. The main point is that even if we allow slightly infeasible solutions, you can have highly superoptimal values. So what is the philosophy? You know, how do we deal with something like this? You know, we want to be practical. We're writing software so that engineers and such can use it. We're not here to tell engineers your problem does not have a solution. Okay, so we want engineers to, but what we should do is tell people that, okay, you know, we are very sophisticated. We will produce solutions that are imprecise. In some form, this has to be communicated. The term approximate is misleading because most people will interpret approximate in a positive way. And in problems of this type, I think this is going to be a step too far. But we can say we are giving you an imprecise solution. You know, you work with it. You tell me what you think. Engineers are never simply going to take a vector and use it. They look at it. They'll play with it. They're not that stupid. So we can trust them on doing an evaluation based on what they think. So that's my practical comment. But what is the real problem here? And now we are going to reach something that I have not brought up before, which is all of these products, Gurobi, Skip, many others. They don't just give you a solution. They also work with a relaxation. The goal of the relaxation is to prove a lower bound. Okay? That's what the solvers are doing. And with a situation like this, a convex relaxation could well prove that the problem that you solve has a bigger value than the solution that you claim to provide. Okay, we provided a super optimal solution. It's quite possible that a convex relaxation will prove that the value of the problem is much bigger than what you claimed. In fact, that convex relaxation could be part of the same package. It may be that you run the package one way, it gives you one answer. If you run the package a different way, it gives you a different answer. And the thing is, so on the one hand, the convex relaxations, those are very high quality relaxations. They are backed by theorems. There's a lot of mathematics. There may be a semi-definite approximation with a very good proof showing that, yes, this semi-definite approximation proves a lower bound to the problem. And these are nonlinear relaxations. The tighter the relaxation, the better it is as per the community. The relaxation may look at a point that is even slightly infeasible and cut it off. It's not that the relaxation cuts it off explicitly. It looks at that point and cuts it off. It's just that the mathematics that supports a relaxation will exclude this vector because it is infeasible. And the relaxation itself is very nonlinear. Moreover, the relaxations, as I said, are themselves, driven by sophisticated formulations, semi-definite, conic. They also may provide some challenges. It's not easy to solve a big semi-definite program. So now we have a case where the lower bound could be suspect. You don't know, did I solve this semi-definite program properly? The upper bound could be suspect because you have infeasibilities. When coupled with the nonlinearities and non-convexities in a high dimensional space, well, you don't know what's going on. And as I'm sure all of you understand, for a non-convex problem, unlike for the convex, especially unlike for the linear case, if you have an infeasible vector, even slightly infeasible, as per the individual constraint violations, it is not going to be simple to correct that vector and make it feasible. In the linear case, yes. In the nonlinear, non-convex case, not at all. Nobody has any idea how to do that. And so now you have a package, you run it two ways. It gives you two different answers that contradict each other substantially. And you don't know which is right and which is wrong. Okay, and so my practical solution, I think, is the only solution. All right, now since we are talking about relaxations, let's get back to the world of mathematics. So what are the relaxations that people have deployed for algebraic problems? And it turns out that there are a number of ideas, common ideas, that were addressed by many authors, usually without giving credit to one another, kind of rediscovered. The main idea, so I think the earliest version is that this McCormick relaxation, which is that if you have a bilinear form, xi times xj, with bounds on the two variables, upper and lower bounds, then you can write a convex hull of the set of values that the bilinear form takes. And it's this, it's a linear system. That's the convex hull of this set over here. And this was proved by, it was proposed by McCormick, and it was proved by these guys. And this was done a long time ago. Huh? Some of you guys might know better than I, early 80s or 70s, maybe even. And it's easily extended to, trilinear forms and so on. And the expressions start to get more and more complicated, but still a polyhedral formulation. This is closely related to what people in the integer programming world called RLT, Cherrellian atoms. Typo, I'll fix it. Cherrellian atoms. And it has a very simple description. Let's say that I have this inequality as part of my system, and I multiply it times this monomial, assuming that we know that it is non-negative. Well, we introduce a variable that represents the product of x1 times x1 times x4, x1 squared times x4. And we introduce a new variable corresponding to x1 times x2 times x3 times x4, and then 5 times x3 times x1 times x4, okay? Now we have new variables. And we do this in every possible way. So for example, we look at all degree 2 expressions, and we multiply our system of algebraic inequalities times every one of those, and we apply this linearization step. And then you have a linear formulation that usually gets coupled with McCormick. You can either, if you have bilinear forms or for the monomials of larger degree, you can apply the constraints that you have observed to those new variables that you create. And there are other heuristic ideas, and also maybe not so heuristic, like if you have two algebraic inequalities, well, you multiply them times one another and you have a similar result. So this is RLT in various flavors. There are many, many versions, many practical issues. How many of these do you actually enforce? How many don't you? Which ones do you enforce? The systems that you get, if you were to enforce all of these, are going to be way too big, linear, but way too big. Too many variables and too many constraints. Another favorite technique is so-called spatial branching, which means branching on a real variable. You take a variable and some value, and you branch either less than or greater than or equal to, or less than or equal to, or greater than or equal to. But however, every time that you do this, you can go to the McCormicks that you have and tighten those. You're improving either the upper bound or the lower bound on some variable. And so whatever formulation that you have gets substantially tightened. And this is done in many ad hoc ways. So a bunch of solvers like Skip, probably Gurobi also has this, and many others have, these are the workhorses, these two things. And they keep you working on a linear space.
Dan, I just wanted to give you a time reminder about 8 more minutes or so.
Oh my God.
I'm not sure.
All right, I'll go extra fast. I
Okay.
want to go to Jen's slide.
Okay.
The other technique is semi-definite programming. Of course, if you form these products, the matrix that has these values has to be positive semi-definite of rank 1. You can restrict this operation to monomials of up to degree d, meaning you form the vector of all the monomials of degree up to degree d on all the variables. It's a big n choose d or more. I forget what the bound was. Something on the order of n to the d monomials. And now you apply what? You create the matrix, which is the outer product of that vector with itself, RLT'd, and now you insist that that matrix should be positive semi-definite. So it's a massive, for any value of d, even d equal to 1, it's going to be, already a non-trivially large matrix. So we enforce that. Moreover, you can take expressions. So here, beta is a particular monomial. Okay, and this is the technique that I described before, where now each of these things will be RLT'd into a new variable that depends on beta. If we were to do this for all beta of degree up to d and form the corresponding vector, so this is one of your constraints times all the beta, x beta for beta of degree up to d, you have a vector now of expressions, and now take the outer product of that vector with itself, okay, and insist that it has to be positive semi-definite. And this is Lasserre's level D moment relaxation. You have a massive semi-definite program, truly massive, difficult to solve. You can show that as this degree of the monomial goes to infinity, the value of the semi-definite program converges to the true value of the problem. Under selected conditions, the convergence is finite, but you may have to go to a degree of these monomials that is much larger, exponentially larger, doubly exponentially larger in the dimension of your problem to begin with. This, from a computational standpoint, this is infeasible, period. But the theory is beautiful, and I would be the first one to say that. Okay. There are problematic issues. I'm running out of time. This is a paper of Japanese people where they constructed a case where the hierarchy, the solvers could not solve the hierarchy and would claim to have basically they would get a suboptimal solution to the SDPs, thereby proving that some bound on the problem was actually optimal, and it was not. And they corrected the problem. This is a very small dimensional. Sorry, I'm gesturing at the screen, but you don't see this. A very small dimensional example with like 3 variables. And they corrected the problem by solving the SCPs with using 1,000 digits of accuracy, literally. This is a paper in the computer science theory community arguing that these, I'm talking about the sum of squares hierarchy for polynomial optimization. Sum of squares, SDPs, you can think of them as the duals of the moment relaxations. That they cannot be solved in polynomial time, even for fixed dimension. Anyway, everybody, not you guys, but everybody in optimization likes to claim semi-definite programs can be solved in polynomial time. Not true. Even when there's a positive statement, there's always an epsilon in there, an annoying epsilon. But even with the epsilon, it's still not true. You have to apply the ellipsoid method, and you have to assume that the conditions for the ellipsoid method hold in terms of this 2 balls of appropriate radii contained and containing the feasible region, that they are polynomial size. The radii can be expressed with polynomial number of bits. For LP, it is true. For STP, not always true. Okay. All right. Oh, I'm totally running out of time. So what I wanted to show is that this system that underlies the small example where Gurobi and Skip were giving the wrong answer, if we were to apply some of these common techniques, RLT and STP, they will prove that this quantity that I call sneaky cannot be 0. Okay, and I'm going to skip. So here I'm quoting Ruth Misner, who is somebody who works on MinLP, has a code called Antigone, very nice. Pietro Bellotti wrote Cohen, also very nice. And I'm combining his technique plus a technique of these guys, Doms and Neumeier, to prove that if you were to apply them, but Ruth pointed out that no code combines these two today yet, then you would get the desired result. And the other version is using branching I had this neat proof to show that if you branch and now use RLT and SDP, you prove a positive lower bound on this sneaky quantity. All right, epsilon feasible solutions. We all would like that. This is what some people might mean. It's a little dangerous. In the LP case, this is okay. In the nonlinear case, you have to be careful because you don't know a priori what the scale is. Okay, if epsilon is much bigger than f of x, then this is very crude. You have to know what f of x will be at the optimum x. And with nonlinear expressions, this is very hard to know. Scaling is hard in nonlinear problems. You can prove, this is an updated version of the, again, this is a sneaky example that is bad. You can prove that unless epsilon is doubly exponentially small, you will not be able to cut off this bad example. Okay, so it's not going to help you in this case. All right, so you've seen this. Back to my theorem. What did I want to do here? Oh, two quadratics. I said, oh, how about two quadratics? Well, there's a theorem also of Robustness, very strong, very nice theorem to show that if you give me two quadratics, you can determine if the system of the two quadratics is feasible in polynomial time. This is a strict result. There's no waffling, no lying. It's correct as stated. And this is tantamount to optimization. If you want to optimize this quadratic subject to that constraint, it amounts to doing binary search over D1, assuming that one of the two. So one of the two has to be positive definite. And then you're doing binary search. But this is actually superseded by something else that was already known, which is the so-called S lemma, which is duality for two quadratics, just two quadratics. If you have two quadratics and the second one has a Slater type condition, then the first one is non-negative whenever the second is, if and only if there's a dual. There's a vector of duals that proves so. And this condition can be written, the red condition can be written as an SDP, in fact, as an SOCP. And now this is polynomially solvable. This is polynomially verifiable, but wait. There's a log of 1 over epsilon term. Now there's an epsilon, it comes back. Okay, in fact, Yin-Yu Ye and apparently Karmarkar proved that the problem can be solved with a dependence on epsilon, which is log of 1 over epsilon. Obviously, the epsilon has to be presented to you in some special way for this result to make sense. I think that the way that, and I have not read Yin-Yu Ye's paper from around 1990 yet. I believe it's an algorithm that just run, there's no epsilon, you just run the algorithm, and after k steps, it has an accuracy which is of the order of 2 to the k digits of the error, 2 to the k digits. And so that is consistent with log of 1 over epsilon. Now, how about more than two quadratics? I have 2 more slides left in the talk, then I'm done. Okay, more than two quadratics. There's a result of Barvinock that says that if I have a system of homogeneous quadratic forms on the unit sphere, then for any fixed number of m, 3, 4, 50, you can check whether the system is feasible in polynomial time. And as a corollary, due to somebody from Columbia, you can show that for any fixed m, you can solve an optimization problem of this form in polynomial time. Okay, now, Barvinock's paper is quite difficult to read. I have attempted it many times. I make progress along different directions. He cites papers from the Russian literature that I would have to go and read. He tells me that indeed it is a polynomial time algorithm in the Turing model. I have no reason not to disbelieve him, but I would like to really grasp that. Now, additionally, Barvinock's paper uses what? It uses Rennegar's algorithm, okay? And he considers a system of algebra. This is an abridged form, one of the theorems in abridged form. Of fixed degree and a fixed number of variables, you can check feasibility in polynomial time, okay? Now, Renneger's paper is also very hard to read. And I'm making progress in reading it. And that concludes my talk. Thank you very much.
It's always hard to figure out how to clap on these things. Thanks so much. Anybody have any questions? Want to open that up? And for those who have to leave, feel free to drop off the call if you have another appointment. But want to pause now for some questions.
It's more or less on time, 5:15.
Yeah.
I did skip a proof.
So I mean, that issue that you pointed out towards the beginning, or that I mentioned about the solver having tolerance. I think the constraint violation was 10 to the -8.
Yeah.
And I think I understood it as saying, your answer is saying that there's like multiple tolerances.
Yes.
Cascading somehow.
That's my guess. Okay, I've written solvers, and you have to do this.
Mm-hmm.
Okay, you cannot have one single tolerance, and it's the same tolerance for every computation.
Mm-hmm.
Otherwise, you'll have a very non-robust algorithm if you do that.
Mm-hmm.
And so, in order to have very high tolerance at the final level of the algorithm, you have to start with an incredibly tight tolerance at the lowest level, which is the linear algebra level.
Mm.
And with floating point computation, that's not going to be possible. Now, you could try to achieve it using extended arithmetic, which is what the Japanese did with this whatever STP code they were using. But STP is convex. It's better behaved. I had this little theoremette on one of the pages showing that for the particular system that I had, you need to have this double exponential accuracy to cut that off, to capture that. And 2 to the 2 to the minus n, or 2 to the 2 to the n digits, that's a 2 to the 2 to the n precision. With n equal to 20, that's already beyond astronomical.
Mm-hmm.
You cannot do it. I mean, never mind extended arithmetic. You need a computer bigger than the universe.
Right.
So that's not going to work. I mean, but what I would like to stress is that there is a practical perspective to all of this. Not get carried away and say, okay, I'm going to quit working on this field because the problems could get very bad. Mm-hmm. I mean, all you have to say is that prepare people for the eventuality that you're providing imprecise solutions. Mm-hmm. Certainly not exact solutions. Nobody should say that they have a system for computing exact solutions for problems like this. That's preposterous. That'll never be true. But even approximate with a very good tolerance, that maybe you cannot guarantee it. You don't know it. You really don't know it. Okay. It's risky to write a package that says, hey, I give you a solution with tolerance 10 to the -6. An engineer might interpret that verbatim, right? They may not watch this talk. So, but you can still say, I hope that my solution is useful to you. And in fact, they can verify they're using Nitro or IPOpt or Gurobi or Skip, that it is useful to them. And the inaccuracies may not be a big deal. And then everything is okay. And then be prepared that now and then they may see something that is a little bit conflicting. From an engineering standpoint, I'm looking at this picture. If you provide this picture to an engineer and say, hey, my feasible solution is the black zone, and I'm giving you this red point, they'll be concerned. They will say, oh, wait a minute, that red point may be very non-robust. And indeed, it is very non-robust. If I perturb the data in my problem a little bit, eventually, at some point, this is going to get cut off all of a sudden. It'll jump to there. And it's isolated. These are all, from an engineering standpoint, these are all very questionable features of this point. Non-robust, isolated, strange out there. Moreover, maybe we discovered that the lower bound cuts it off. What's going on? Low-dimensional problem like this, it's easy to interpret and say what it is. For a problem like the one I was going to run before and I ran out of time with, with a million variables. Who knows what's going on?
Right.
Okay, you really don't know. And it's not worth pursuing. Just be reasonable. Yes.
Yeah. So I see there's a question by Mike Todd and then Adrian. I just wanted to ask just really quick follow-up to what you said. Is this motivation then for providing a family of solutions with perturbations of your constraints to a practitioner or no?
No, I would say no, because you won't have time. Okay. Yeah. These are the bigger runs take too long. I mean, but yes and no. Yes and no in the sense that nobody in an engineering context wants to solve one problem. They'll be solving. So in this power setting, they might be solving these every 5 minutes. And so if one of them is a little wrong, it's okay. It's whether on average, or most often the code is working out okay, and it's doing something they could not do otherwise. That's when the code is really useful. And the codes really are very useful for this particular problem class. It's impressive. I wish, like I said before, I wish I could run MATLAB and I would run Nitro on the biggest AC OPF problem that I have. And as far as I get, it is computing something that's very, very close to the true optimum. I can compute a lower bound on the optimum. Of course, now me wearing my other hat, I'm expecting that all these solvers have worked correctly. But assuming that they did, the lower bound nearly matches the upper bound. And it's magical because it's such a big nonlinear problem. And I have no other way, and no other way is known, by the way, to get a good solution to these big ACOPF problems other than the log barrier solvers. There's no other way for the big ones, The little ones, yes.
I guess Mike Todd and then Adrian.
Hello, Mike.
So, hi, Dan. So a couple of things. I think, first of all, engineers certainly know about different constraints, which ones are hard, which ones are soft, which ones have data that's imprecise, which ones have constants like 1 and 2 that are really hard and they need to be satisfied. And I think you just mentioned this problem putting in the penalties, but it's absolutely clear that if you put in the log barrier, then you're more likely to be able to achieve feasibility and suboptimality, but at least see where you are. But I think maybe the bigger question is, I think we know a lot about the linear case because of backward error analysis. And I think we need backward error analysis for polynomial systems.
Correct.
And so Jim is here, he can tell us about that. But just having a solution that's given to you by log barrier or some sort of robust optimization is lots of solutions to present to the engineers and get them to look at those solutions.
I should add that this particular aspect of the practice is changing as we speak. Today in the strict practice, if you go and talk to engineers, they know that they can only run this problem occasionally. They don't trust it. They run a linear approximation. This is what gets done in the practice, linear, and they know that the linear approximation is poor, but it's good enough. There's pressure to move to the fully nonlinear setup, and this is why this competition was set up to really tackle realistic instances that are large and show that it can be done. But yes, it'll be fun to see what happens moving forward. Now, if you were to talk to Ian Hiskins, this is this Australian engineer I mentioned before, he will argue from an engineering standpoint that if you have a power grid or power system, as he would say, that is safely set up and operating in a safe mode, that near the optimum of this very nonlinear problem, there's a region that is flat and very convex. This is his language. And so log barrier solvers are, if they're likely to get there, or if they happen to get there, they will converge to something of high quality. But if you further chat with Ian, he will agree that if you're doing what people are doing today, which is what we might call adversarial analysis, where you imagine that this power system is being stressed in some form, that some of the demands are changing and this and that is changing. And you're looking at many instances, one after the other, that you'll run into instances that in fact, where the grid is in fact not in such a safe and stable operative mode. And you're relying on the computation to tell you that, okay? And it's no good if the computation fails to converge and simply says, I cannot run, which happens for these log barrier solvers. They just say, oh, I couldn't run. I ran into trouble. Bye-bye. So that's the important part moving forward. But yes, I agree with Mike. You know, there's a further need for more precision in the language and the metrics and so on. I don't want to paint a picture that is overly dire. You know, as I said before, these codes and log barrier solvers are extremely useful. It's not that they're useless. They work most of the time. It's just that we don't know. And solvers like Skip have IPI that is run to get solutions, and they also have the relaxation, and they're running together. Okay, so a solver like Skip could find itself in a situation where, as they add more technology to the lower bound, so the relaxations, that they may someday cut off the optimum that they computed. This could happen, and there are a lot of people working on the relaxations today. So it's not an absurd point. And today nobody knows. I would say nobody knows. Yes, somebody else had a question.
Adrian has the next question.
Yeah.
Sure. Hi, Dan. By the way, I feel like I'm being interrogated by your desk lamp there behind you. So, So yeah, so it's kind of a related question to Mike's and to something that you said. So you know, Nick Trefethen has this sort of kind of extreme saying, as is common to him, that if you're an engineer and you think you want to compute an eigenvalue of a real matrix, then you might be smart to first make a random perturbation and then compute the eigenvalue.
Yeah.
And so what I wonder, you know, I mean, is the same thing true here? So you know, if you take one of your problems and you're an engineer, you know, wouldn't you be smart first to make a small random perturbation to the real data and then solve it? And might that fix some of this?
That's an experiment worth conducting. I don't know what will happen. I sense that in the situations where let's say the log barrier solver or whatever solvers, I should say that in the industry they've had their own homemade log barrier like solvers for a long time. I don't think that they're as careful with the linear algebra, but because they wrote them, they have a lot of inside knowledge, and you'll have something like a big company like Siemens or General Electric that will work with a utility very closely, and effectively they will craft a special version of their code to their data. Okay, and so it runs well after many trials and so on. But if you ask an engineer, you know, what is a situation of stress? A situation of stress is one where the grid is operating well, and all of a sudden you lose a generator. And after losing a generator, it may be the case that the system remains feasible, but the way that the voltages are set up and the way that power flows is very different, and you've never seen it before. And the solver cannot find it. The solver runs and says, I cannot converge. In fact, the solvers, the language that they use, maybe they didn't invent the language. They'll say that they diverged. I'm diverging, and then the solver quits. In a situation like that, I don't think that a random perturbation will help. It really is something more profound that is happening. Okay, and indeed, in this case, I should do it in this case. Where is it? In that case, I don't think that the random perturbation will work. What I did do is I tried changing. What did I do? Oh, I put a lower bound on sneaky. And at what point does the solver get to the right value? And it was somewhere near 10 to the minus 4 in this case. From 10 to the minus 4 plus a hair, then the solver works correctly. 10 to the minus 4 minus a hair, no, it still gives you the wrong answer. And the thing is that 10 to the minus 4, whereas the solver wanted to set it to like 10 to the minus 8, I think. It's not really random. I mean, one question here actually is, what is random? What is the right scale for a random perturbation, right?
Yeah, I would say if you're an engineer, 10 to the minus 4 is good, right? It's like 4 digits. Like, that's good. That kind of.
Yeah, but you would have to guess that.
Sure. Yeah, no, I understand. Yeah, but this may be one reason that they like the linear approximations instead of the original problems, right? So it's the same.
Yeah, the linear approximation. I mean, they like it for many reasons. It's utterly reliable. You can combine it with binary variables, which sometimes they do. And moreover, when in pure LP form, they use the duals. The duals are the prices that people get charged. People meaning the duals are the prices that the utilities get paid for generating power. I don't know if how would you derive a theory of duality for the non-convex problem? And so actually that's an issue right now that many people are pushing for the nonlinear formulations, but then the economists are saying, well, our business is trashed if we do that. We need to find some scheme to compute prices that makes sense at some level. Anyway,
thanks.
But I mean, I appreciate all of these things, all valid. Once again, I don't want to portray an overly dismal picture. I'm approaching this from many directions. I'd like the very theoretical direction. There are all these fundamental questions. Well, Jim probably knows that the underlying mathematics is not really linear algebra. It's algebra. It's related to very modern themes and pure mathematics, not too distant. The issue of computing roots of polynomials quickly, the issue of a symbolic computation for denesting radicals, which is one of the approaches that one might use. This is very closely related to very modern themes in algebra. Themes that are pursued by mathematicians and mathematics departments. And so this is all very cool and very interesting. I also, of course, like the computational perspective. How do you deal with this? How do you know when you have a problem? And how do you get these things to go quickly? I really feel bad that I could not run Nitro or IPOpt, because the log barrier on the biggest problem that I have, which will be a formulation with approximately 1 million variables, it solves it in about 3 minutes on my laptop. And as far as I can tell, modulo the rest of my talk, it has the optimum. Very impressive, very nice.
So I don't see any further questions, but I know that there's a PhD student meeting with you. All right, thanks so much, Dan.
Thank you. Bye-bye.
Thank you.
Bye.